Every particle in the universe carries a label. Not a physical tag you could peel off and examine under a microscope, but something deeper, something built into its very identity. We call it electric charge. You already know the word. You've felt it when a shock jumps from a doorknob to your fingertip. You've seen it in lightning bolts and battery terminals. But here's the question almost nobody thinks to ask. What is charge actually made of? Is it some kind of substance hidden inside an electron? A tiny packet of electrical stuff? Physics has measured charge with breathtaking precision, down to a billionth of its value. But when you push past the measurements and ask what charge fundamentally is, the answer is stranger than anything you'd expect. Charge is not a thing. It is not made of smaller pieces. And understanding what it really is changes how you see every force and every particle in existence. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. You felt charge before. Maybe not with that word attached to it, but you felt it. You shuffle across a carpeted floor in your socks, reach for a metal doorknob, and a tiny spark jumps from your fingertip. There's a snap, a brief sting, and for a fraction of a second, you see a miniature bolt of lightning bridging the gap between your hand and the metal. That spark is real. Something happened. Something moved from you to the doorknob, or from the doorknob to you in that instant. And if you've ever pulled a wool sweater over your head in a dark room, you might have seen the faint blue crackles dancing across the fabric. You might have heard the soft popping sounds. Your hair stands on end, reaching toward the sweater as if drawn by invisible strings. These are some of the most familiar electrical phenomena on Earth. Humans have noticed them for thousands of years. The ancient Greeks discovered that rubbing amber with fur would cause the amber to attract small objects, bits of straw, feathers, flakes of dried leaf. The Greek word for amber is electron, and that word eventually gave us electricity, electron, and electronics. But knowing the name of something is not the same as understanding what it is. So what is actually happening when you build up charge by shuffling across a carpet? The standard explanation you hear in school goes something like this. When you rub two materials together, electrons transfer from one surface to the other. One surface ends up with more electrons than it should have, making it negatively charged. The other surface loses electrons and becomes positively charged. The imbalance creates an electric force, and when you touch the doorknob, the excess electrons rush across the gap to restore balance. That explanation is correct as far as it goes. Electrons really do transfer between surfaces. The spark really is a rapid movement of charged particles through the air. But notice what this explanation doesn't tell you. It tells you that electrons moved. It tells you that surfaces became charged. But it never tells you what charge itself actually is. It uses the word charge as though you already know what it means, as though it's obvious. And most people, when they hear the word charge, form a picture in their minds. They imagine charge as some kind of stuff, some kind of electrical substance that lives inside particles. They picture an electron as a tiny container holding a little packet of negative charge, the way a jar might hold a little packet of salt. They imagine that when you charge a balloon by rubbing it on your hair, you're transferring little units of this electrical substance from your hair to the balloon. You're moving stuff around. This picture feels natural, it's intuitive, and for the most part, it works. If you think of charge as a fluid or a substance, you can explain a lot of electrical phenomena correctly. Current flows like water through pipes. Charge accumulates on surfaces like water pooling in a basin. Charge transfers from one object to another, like pouring liquid between cups. The fluid picture works so well that it dominated scientific thinking for over a century. Benjamin Franklin, one of the most important early researchers of electricity, explicitly described charge as a fluid. In the 1740s and 1750s, Franklin proposed that electricity was a single invisible fluid present in all matter. When an object had more than its normal share of this fluid, Franklin called it positively charged. When it had less than its normal share, he called it negatively charged. The spark you feel at the doorknob was, in Franklin's view, this fluid rushing from where there was too much to where there was too little. This was a productive model. Franklin used it to explain a wide range of electrical phenomena. He explained how a Leyden jar stores charge. He explained how lightning is an electrical discharge, famously connecting that idea to his experiments with kites during thunderstorms. His convention of positive and negative charge is still the one we use today, over 270 years later. And across the Atlantic, other researchers developed a competing two-fluid model. Instead of one fluid with excess and deficit, they imagined two separate fluids, one positive and one negative. Objects became charged when they had an imbalance between these two fluids. Both models worked reasonably well for the experiments available at the time. They made correct predictions. They explained observations. And they both treated charge as a physical substance, something material, something that exists as a thing in its own right, flowing from place to place, accumulating in objects and creating forces. But here's the problem. Both models were wrong. Not wrong in their predictions, which were often accurate enough for the experiments of that era. Wrong in their fundamental picture of what charge is. Charge is not a fluid. Charge is not a substance. Charge is not a material thing that flows from one place to another like water or air. And understanding why requires a shift in thinking that is more subtle and more profound than it might first appear. Let me explain what charge actually is, and to do that, I need to talk about the difference between a thing and a property. Consider the color of a red apple. The redness is a property of the apple. It describes something about the apple, specifically how the apple interacts with light. The apple absorbs most wavelengths of visible light, but reflects red wavelengths back to your eyes. That's what redness means. But nobody thinks redness is a substance inside the apple. Nobody imagines that if you cut the apple open, you'd find a little pocket of red stuff hidden in the core. Nobody thinks you could scoop the redness out of one apple and pour it into a different apple. The redness isn't a thing. It's a description. It tells you something about how the apple behaves, how it interacts with light. But it has no independent existence apart from the apple. Now think about mass. Mass is a property of objects. A bowling ball has more mass than a tennis ball. Mass tells you how strongly an object resists acceleration when you push it, and how strongly it creates and responds to gravitational fields. But mass is not a substance inside the bowling ball. You can't open up the bowling ball and find the mass sitting there as a separate ingredient. The mass is not made of something. It's a property of the bowling ball as a whole, a description of how the bowling ball interacts with gravity and with forces that try to change its motion. You would never ask, what is the mass of a bowling ball made of? That question doesn't make sense, because mass isn't made of anything. Mass is a property, a fundamental characteristic of the object itself. Charge is the same kind of thing. Electric charge is a property of certain particles. An electron has charge, a proton has charge. These charges describe something about those particles, specifically how they interact with the electromagnetic field. But charge is not a substance sitting inside the electron. You can't open up an electron and find charge in there like a prize inside a cereal box. You can't extract the charge from an electron and leave behind an uncharged electron. The charge is not a component. It's not an ingredient. It's not a smaller piece that makes up the electron. It is one of the defining characteristics of what an electron is. Take the charge away, and you no longer have an electron. You have something fundamentally different, something that doesn't exist in our universe. This distinction matters enormously, and it's one that trips up a lot of people, including many who study science for years. We are so used to thinking about the world in terms of substances and ingredients that we instinctively want to make everything into a thing. We want charge to be made of something, just like a cake is made of flour and sugar and eggs. But charge doesn't work that way. Charge is a label, a quantum number, a fundamental tag that tells the universe how this particle relates to the electromagnetic field. An electron carries negative charge, the same way a particular quark carries a property called color charge in quantum physics. These aren't substances you could hold in your hand or examine under a microscope. They're properties that determine how particles participate in certain interactions. Let me push this further, because the misconception runs deep. When people hear that rubbing a balloon on hair transfers charge, they often imagine that the charge was sitting on the hair and then moved to the balloon, like transferring sand from one bucket to another. But that's not quite right. What actually transfers is electrons. Whole electrons, complete particles. The electrons were part of the atoms in your hair, and after rubbing, some of those electrons ended up on the balloon's surface. The charge didn't move independently across some gap. The electrons moved, and because electrons have charge as one of their fundamental properties, the charge went with them. The charge didn't flow from your hair to the balloon like a liquid. Particles with the property of charge relocated from one surface to the other. This might seem like a trivial distinction, almost pedantic, but it changes the entire conceptual picture. In the old fluid model, charge is primary and particles are secondary. The charge flows and particles are just its carriers, the way a bucket is just a carrier for water. In the correct picture, particles are primary and charge is a property they carry. Electrons exist as fundamental particles, and one of their properties happens to be negative electric charge. The electron isn't a container for charge. The electron is a fundamental entity, and charge is one of the numbers that describes it. Here is another way to see why the substance picture fails. If charge were a substance, you'd expect it to be divisible. You'd expect that you could take some amount of charge and split it into smaller amounts, the way you can divide a cup of water into 2 half cups. But that's not what we find in nature. Every isolated charge ever measured is an exact whole number multiple of a single fundamental unit. You never find half a unit of charge floating around. You never find 1/3 or 2/5 or any other fraction. Charge comes in indivisible chunks. The smallest unit of free charge is the charge carried by a single electron or a single proton. This alone should give us pause. If charge were a fluid, a continuous substance, you'd expect to be able to have any amount of it. You'd expect continuity. You'd expect to find charges of any size, just as you can have any volume of water. But charge is discrete. It comes in exact, identical packets. This is a strong hint that charge isn't a substance at all, but a property that takes only specific values, like the energy levels of an atom, rather than the temperature of a room. And those packets are perfectly identical. Every electron in the universe carries exactly the same charge. Not approximately the same, not almost the same, exactly the same to every decimal place we've ever been able to measure. The charge on an electron is negative 1.602176634 times 10 to the negative 19 coulombs. That is the value, and every single electron in the entire observable universe carries that exact charge. The electron in your fingertip carries the same charge as the electron in a distant galaxy 10 billion light-years away. There is no variation, no manufacturing tolerance, no slight differences from one electron to the next. Every electron is perfectly identical to every other electron in this regard. This uniformity is extraordinary when you stop and think about it. If charge were a substance, if it were some kind of fluid that got poured into electrons during their formation, you'd expect some variation. No manufacturing process in the macroscopic world produces perfectly identical products. Even the most precise factory introduces tiny variations. But electrons aren't manufactured objects, they're fundamental particles. The charge is part of what defines them as electrons. Every electron has the same charge, because if a particle didn't have that exact charge, it wouldn't be an electron. It would be something else entirely. This brings up another important distinction that often gets muddled in everyday conversation and even in some textbooks. The difference between electric charge and electric current. People frequently confuse these two concepts, and the confusion stems directly from that same misleading fluid picture. In the fluid model, charge is the fluid and current is the fluid flowing, like water moving through a pipe. But that's misleading. Electric current is the organized movement of charged particles through a material. When you turn on a lamp, electrons in the copper wire begin to drift in one direction, pushed by the electric field created by the voltage difference between the two terminals of your power source. That drift of electrons constitutes the current. Current is measured in amperes, named after the French physicist who studied it extensively, and 1 ampere means roughly 6.24 times 10 to the 18 electrons passing a given point in the wire every second. That's a staggering number of electrons, a flow of particles far too numerous to count individually. But here's the crucial point. The current is not charge flowing like water through a pipe. The current is particles moving, particles that happen to have the property of charge. The charge doesn't flow independently of the particles. The electrons move through the wire and they bring their charge with them because charge is their property. Charge and electron aren't two separate things traveling together in the wire like a passenger riding in a car. They're one thing, an electron, and charge is one of its attributes. You can't separate the charge from the electron any more than you can separate the mass from a bowling ball. This also helps clarify why saying charge is made of electrons is wrong, a mistake that shows up surprisingly often. That would be like saying height is made of tall people. Height is a property that people have. Similarly, charge is a property that particles have. Electrons carry charge, protons carry charge, but charge isn't composed of those particles. The relationship goes the other direction. Particles have charge, not the other way around. Charge is a feature of each individual particle, a feature that every particle of a certain type shares exactly. Now, if charge isn't a substance, if it's a fundamental property rather than a material ingredient, the natural next question is, what does this property actually do? What is charge for? Why does it matter that an electron carries charge while, say, a neutrino does not? The answer is both simple and far-reaching. Charge determines whether and how strongly a particle interacts with the electromagnetic field. That's it. That's the job of charge. It's a coupling, a connection between the particle and one of the fundamental fields of nature, a measure of how much a particle talks to the electromagnetic field and how loudly the electromagnetic field talks back. A particle with charge produces electromagnetic effects all around it. It creates an electric field radiating outward from its position. When it moves, it also creates a magnetic field swirling around its path. It can emit and absorb photons. It pushes and pulls on other charged particles across distances. It responds to external electric and magnetic fields by accelerating, curving, gaining or losing energy. All of these behaviors, everything we associate with electricity and magnetism, every spark and every signal and every beam of light interacting with matter, come from this single property: charge. A particle without charge does none of these things. A neutrino, for instance, carries no electric charge. It passes through electromagnetic fields as though they simply aren't there. It doesn't create electric or magnetic fields of its own. It doesn't attract or repel electrons or protons. It doesn't emit or absorb photons through electromagnetic interaction. It is electromagnetically invisible. The electromagnetic field, which dominates so much of everyday experience, which holds your atoms together and carries the light entering your eyes right now, has absolutely no grip on a neutrino. A neutrino could fly straight through a wall of solid lead a light year thick and come out the other side without interacting once, because it lacks the one property that would allow it to feel the electromagnetic field. That property is charge. This is what makes charge so fundamental. It's not a thing. It's not an ingredient you can hold or weigh or pour. But it controls one of the most important interactions in the entire universe. Without charge, there would be no atoms, because atoms are held together by the electromagnetic attraction between positively charged protons in the nucleus and negatively charged electrons surrounding it. Without charge, there would be no chemistry, because chemical bonds are electromagnetic in nature. Without charge, there would be no light in the way we experience it, because the emission and absorption of light depends on charged particles interacting with the electromagnetic field. Without charge, your body wouldn't exist. Every cell, every protein, every molecule in your body is held together and communicates through electromagnetic forces. The signals in your nerves are movements of charged particles. The energy in your cells comes from electromagnetic reactions between charged atoms. And yet, charge itself is not a physical object you can point to. It has no size. It has no shape. It has no color or texture or weight of its own. It's more like a setting on a dial than a lump of material. An electron's charge setting is at -1, in units physicists call the elementary charge. A proton's setting is at +1. A neutrino's setting is at 0. And these settings are permanent, absolute, written into the fabric of reality. You cannot adjust them. You cannot turn the dial. You cannot make an electron slightly more negative or slightly less negative. The value is fixed, built into the very identity of the particle, as certain and unchanging as anything in physics. This picture might feel unsatisfying at first. When you ask what something is made of, you expect an answer that involves smaller pieces. Atoms are made of protons, neutrons, and electrons. Protons are made of quarks. Water is made of hydrogen and oxygen. We're used to answers that decompose things into components. But charge doesn't decompose into components. It's not made of anything smaller. It's fundamental. And in physics, fundamental means this is where the chain of explanation reaches bedrock. Not because we're too ignorant to dig deeper, but because the evidence strongly suggests there may not be a deeper level to dig to. Charge is a brute fact about how the universe works, a basic feature of certain particles that does not reduce to anything else. This might sound like a surrender, like physicists throwing their hands up and saying, "We don't know." But it's actually the opposite. It's one of the most precise and hard-won conclusions in all of science. Physicists have spent well over a century probing the structure of matter at smaller and smaller scales. They've built accelerators that smash particles together at speeds approaching the speed of light. They've measured properties of fundamental particles to 10, 12, even 14 decimal places of accuracy. And at every level, charge behaves as a fundamental property. It doesn't break apart under scrutiny. It doesn't reveal hidden internal structure. It doesn't show any hint of being composed of something else. It simply is. Think about how remarkable that is. In almost every other domain of nature, when we look more closely, we find more structure. Rocks are made of minerals. Minerals are made of crystal lattices of atoms. Atoms are made of subatomic particles. Subatomic particles are made of quarks and gluons. At every level, there's more detail, more complexity, more layers waiting to be uncovered. But charge doesn't follow this pattern. It sits at the bottom of the hierarchy. It's one of the irreducible properties that define what a particle is. And the fact that every electron everywhere shares exactly the same charge, that this property is perfectly uniform across the entire observable universe, across billions of light years of space and billions of years of time, tells us something profound about the nature of reality itself. Whatever the fundamental rules are that govern the creation of particles, those rules are absolute. They don't allow variation. They don't permit imperfection. They produce perfect copies, every single time, everywhere, for the entire history of the cosmos. This perfection is not something we observe anywhere in the macroscopic world. No two snowflakes are alike. No two fingerprints match exactly. No two manufactured products are perfectly identical down to the last atom. But every electron is identical to every other electron. Every proton is identical to every other proton. Their charges are identical to a degree of precision that far exceeds anything we encounter in everyday life. And this uniformity points to something deeper. Particles with their fixed charges aren't objects that were assembled from parts on some cosmic assembly line. They're excitations of quantum fields, ripples in underlying fields that permeate all of space. Every electron is identical to every other electron, because every electron is a ripple in the same electron field. Just as every wave in the ocean is made of the same water and obeys the same wave equations, every electron is a vibration in the same field and carries the same properties. The charge of that ripple is determined not by what was poured into it, but by the nature of the field itself. We're about to explore that field, the electromagnetic field, and what it truly means for a particle to couple to it. We're going to see how charge isn't just a static label sitting passively on a particle, but an active connection that governs real forces in real time, mediated by particles of light. But before we go there, let me make sure one thing is absolutely clear from everything we've discussed. Charge is real. It's not imaginary. It's not just a bookkeeping label we invented for convenience. It has measurable, physical consequences. It determines real forces between real particles. It governs the structure of every atom, every molecule, every material in existence. It shapes the behavior of everything from the chemical reactions in your cells to the lightning bolts that split the sky during a thunderstorm. Charge is as real and as consequential as anything in physics. But it's not a substance. It's not a fluid. It's not a material. It's a fundamental property of particles that controls their relationship with the electromagnetic field. It cannot be divided. It cannot be extracted. It cannot be separated from the particle that carries it. It is intrinsic, permanent, and identical across every particle of the same type in the known universe. And that distinction between a property and a substance, between a fundamental label and a physical ingredient, is the key that opens up everything that follows. Because once you stop thinking of charge as a stuff and start thinking of it as a coupling, as a connection between a particle and a field, the entire electromagnetic world begins to make a different and much deeper kind of sense. We've established that charge is not a substance hidden inside particles. It's a fundamental property, a permanent label that certain particles carry. But a property needs to do something. A label is meaningless unless it connects to some real interaction in the physical world. So what does charge actually connect to? What is the thing out there in the universe that charge is a coupling to? The answer is the electromagnetic field. And the electromagnetic field is not an abstraction. It's not a mathematical convenience. It's not a metaphor or a visualization tool. It is one of the most real things in the universe, as physically present as the ground beneath your feet, though far more subtle and far more pervasive. Understanding this field, and understanding what it means for charge to couple a particle to it, is where the true depth of the concept begins to reveal itself. Let's start with what a field is in physics, because the word gets thrown around a lot, and most people have a vague picture at best. In everyday language, a field is an open expanse of grass, or a domain of study, or an area where something happens. In physics, the word means something very specific. A field is a physical quantity that has a value at every point in space and at every moment in time. Temperature is a simple example. At every location in a room, there's a temperature. Near the heater, it might be warmer. Near the window, it might be cooler. The temperature varies from point to point, but at every single point, there's a definite value. That collection of values spread throughout space is a temperature field. The wind is another example. At every point in the atmosphere, the air has a speed and a direction of motion. That's a velocity field. It changes from place to place and from moment to moment, but at every point, there's a value. The electromagnetic field works the same way, except instead of temperature or wind speed, the quantity at each point is an electric and magnetic influence. At every location in space, right now, there is an electromagnetic field. It has a value. It has a direction. It has a strength. Even in what you'd call empty space, the electromagnetic field is there. Not as a potentiality, not as a readiness to spring into existence. It's already there. It permeates everything. It fills the gap between atoms, the void between stars, the space between galaxies. There is nowhere in the universe where the electromagnetic field does not exist. This idea took centuries to develop. For most of scientific history, forces were thought of as actions at a distance. Two charged objects attract or repel each other across empty space, and that was that. There was nothing in between. The force just somehow reached across the gap. Isaac Newton himself was uncomfortable with this idea when he formulated his law of gravitation. He called action at a distance philosophically absurd, but he couldn't come up with a better explanation, so he left the question open. The same discomfort lingered for electricity and magnetism. How does one charged particle know the other is there? How does the force reach across empty space? What carries it? Michael Faraday, working in the 1830s and beyond, provided the crucial insight. Faraday was largely self-taught, with almost no formal mathematical training, but he had an extraordinary physical intuition. While studying electric and magnetic phenomena, he developed the concept of lines of force. He imagined invisible lines radiating outward from charged objects and magnets, filling the space around them. These lines weren't just visualization aids. Faraday believed they represented something physically real. The space around a charged object wasn't empty. It was filled with these lines, this influence, this field. This was a radical departure from the prevailing view. Most physicists of Faraday's era thought the lines of force were just a useful picture, a way of visualizing something that was really just action at a distance. But Faraday insisted the field was real. The influence filling space was a genuine physical entity, not a mathematical shortcut. He couldn't prove it with the mathematical tools he had, but his intuition was correct. James Clerk Maxwell, working in the 1860s, took Faraday's intuition and gave it mathematical form. Maxwell wrote down a set of equations, 4 equations that describe how electric and magnetic fields are created by charges and currents, and how those fields interact with each other. Maxwell's equations are among the most important equations in all of physics. They unified electricity and magnetism into a single framework, showing that these two forces are not separate phenomena, but two aspects of one underlying field, the electromagnetic field. But Maxwell's equations did something even more remarkable. They predicted that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. If you disturb the electromagnetic field in the right way, the disturbance propagates outward through space as a self-sustaining wave. An oscillating electric field creates a magnetic field, which creates an electric field, which creates a magnetic field, on and on, leapfrogging through space at a specific speed. Maxwell calculated that speed from the constants in his equations and found it matched the measured speed of light. Light, Maxwell realized, is an electromagnetic wave. The light entering your eyes right now is a ripple in the electromagnetic field, a vibration propagating through the very same field that charged particles interact with. This was one of the greatest unifications in the history of science. Optics, the study of light, and electromagnetism, the study of charged particles, were suddenly the same subject. Heinrich Hertz confirmed Maxwell's prediction experimentally in 1887 by generating and detecting electromagnetic waves in his laboratory. The field was real. It carried energy. It could propagate through empty space. It wasn't an abstraction or a mathematical convenience. It was a genuine physical entity filling the universe. And charge was the key that unlocked a particle's connection to it. And this is a crucial point that deserves emphasis. The electromagnetic field doesn't just exist as a backdrop, waiting for charged particles to do something interesting. The field itself carries energy. It carries momentum. It is a physical thing in its own right, independent of the particles that create and respond to it. When a beam of light crosses the vast emptiness between a distant star and your eye, there are no charged particles along the way. The photons are not being passed from one charged particle to another like a bucket brigade. The light is a disturbance in the electromagnetic field itself, propagating through space on its own, carrying energy through regions that contain no matter at all. When that light hits a solar panel and generates electricity, the energy didn't come from the panel, it came from the field. The electromagnetic field delivered energy across millions or billions of kilometers of empty space. Energy that originally came from charged particles in the star that traveled independently through the field long after leaving those particles behind. The field is not just a way of describing how charges interact with each other. It is a thing in itself, with its own energy, its own momentum, its own physical reality. And charge is what lets a particle reach into this field, disturb it, draw energy from it, or pour energy into it. So now let's talk about what coupling means, because this is the central concept. When physicists say charge is a coupling to the electromagnetic field, they mean charge is the property that determines whether and how strongly a particle interacts with this field. It's like a volume knob. Charge sets the volume of the conversation between a particle and the electromagnetic field. If the knob is turned up, the particle and field interact strongly. If the knob is at 0, the particle and field don't interact at all. An electron has charge. Its volume knob is turned to a specific setting, -1 elementary unit. This means the electron is connected to the electromagnetic field. It produces disturbances in the field around it. These disturbances are what we call the electron's electric field. They radiate outward from the electron in all directions, getting weaker with distance, but never completely vanishing. Wherever the electron goes, it drags this field disturbance with it, like a wake trailing behind a boat moving through water. When the electron moves, it also creates a magnetic field, a swirling pattern of magnetic influence around its path. And when the electron accelerates, when it changes speed or direction, it sends ripples outward through the electromagnetic field. Those ripples propagate at the speed of light. Those ripples are electromagnetic radiation. Those ripples are light. This is worth pausing on. When an electron accelerates, it creates light. Not metaphorically, literally. Every photon of light ever produced in the universe was created by a charged particle changing its state in some way. The glow of a candle flame comes from electrons in excited atoms, dropping to lower energy levels and releasing photons. The light from your phone screen comes from charged particles being driven back and forth in tiny circuits, emitting electromagnetic radiation. The warmth of the sun comes from nuclear reactions in its core that create charged particles which interact with the electromagnetic field, producing the photons that eventually reach Earth's surface 8 minutes later. Every single source of light in the universe traces back to charged particles interacting with the electromagnetic field. And the strength of that interaction, the brightness of the light produced, the force exerted on other charges, the energy radiated, all of it depends on charge. The larger the charge, the stronger the coupling, the more vigorous the interaction. A particle without charge doesn't do any of this. The neutrino, as we discussed, is the clearest example. Its coupling to the electromagnetic field is exactly zero. Its volume knob is turned all the way off. But notice something subtle and important about what coupling means. It isn't simply on or off, like a light switch. Charge comes in magnitudes. A particle with a larger charge couples more strongly to the electromagnetic field than a particle with a smaller charge. It radiates more intensely when it accelerates. It feels a greater force in the same electric field. Every electromagnetic effect is amplified. This means charge doesn't just open the door to electromagnetism, it determines how wide that door swings. How brightly a particle radiates when it changes speed or direction, how strongly it pushes and pulls on nearby charges, how fiercely it responds to external fields. The volume knob doesn't just have an on position and an off position, it has a specific setting, and that setting controls every aspect of the particle's electromagnetic existence. But the story goes deeper, because in the quantum world, fields don't just sit there as smooth, continuous backgrounds. Fields are quantized. They come in discrete packets, and the packet of the electromagnetic field is the photon. This was one of the great discoveries of 20th century physics. Light is not just a smooth wave rippling through the electromagnetic field. Light is made of individual particles, photons, each carrying a specific amount of energy determined by its frequency. Albert Einstein proposed this in 1905, building on Max Planck's earlier work. Einstein showed that light behaves as if it's made of discrete units. These units are the quanta of the electromagnetic field. Every time a charged particle emits light, it emits one or more photons. Every time light is absorbed by a charged particle, it's absorbed one photon at a time. This means the electromagnetic field, the field that charge couples particles to, is itself a quantum entity. It's not a smooth, classical background. It's a quantum field capable of being excited into discrete particle-like states. Those particle-like excitations are photons. And here's the stunning part. In the quantum picture, forces between charged particles are mediated by the exchange of photons. When two electrons repel each other, when they push apart because they have the same sign of charge, the mechanism behind that repulsion is the exchange of photons between them. Let me walk through this carefully, because it's one of the most beautiful ideas in all of physics. In classical physics, in the picture Maxwell and Faraday developed, two charged particles interact through the electromagnetic field. One particle creates a field, and the other particle feels that field. The field is the intermediary that carries the force from one particle to the other. But in quantum physics, this picture gets refined. The electromagnetic field between the two particles is quantized. The interaction between the particles is described not as one particle feeling the other's field, but as the particles exchanging quanta of the field, exchanging photons. Imagine two ice skaters standing on a frictionless ice rink facing each other. One skater throws a heavy ball to the other. As the first skater throws, the recoil pushes them backward. When the second skater catches the ball, the impact pushes them backward too. The net effect is that the two skaters move apart. They repel each other by exchanging the ball. This is a rough analogy for how photon exchange produces repulsive forces between like charges. The analogy breaks down in many ways. Real photon exchange is a quantum process, not a classical throw and catch. And the analogy doesn't naturally explain attractive forces between opposite charges, which require a more careful quantum mechanical treatment. But the core idea captures something essential. Forces between charged particles arise from the exchange of photons. These photons that mediate forces between charged particles are sometimes called virtual photons, because they aren't the same as the photons that travel from a lamp to your eye. Virtual photons exist only during the interaction. They aren't directly observable. They don't travel from a source to a detector the way light does. They flicker into existence during the brief moment when two charged particles interact, carry the force between them, and then vanish. They're permitted by the uncertainty principle, which allows energy to be borrowed for brief moments as long as the books balance in the end. You can't catch a virtual photon on camera. You can't trap one in a bottle. But their effects are measurable, precise, and confirmed by some of the most accurate experiments in the history of science. This deserves a closer look, because virtual photons are one of those concepts that can seem like a cheat, like physicists invented an invisible particle to explain something they couldn't otherwise account for. But virtual photons are a direct consequence of the uncertainty principle applied to the electromagnetic field. The uncertainty principle doesn't just apply to particles, it applies to fields. At every point in space, the electromagnetic field has a value, and that value fluctuates. It has to. The uncertainty principle forbids the field from sitting perfectly still at exactly zero energy. There must be fluctuations, brief, borrowed bursts of energy that appear and vanish on timescales so short that the energy bookkeeping of the universe stays balanced. Virtual photons are these fluctuations given a name. They aren't invented to patch a hole in the theory. They fall out of the mathematics automatically the moment you combine quantum mechanics with the electromagnetic field. And the effects of these fluctuations aren't hypothetical. They shift atomic energy levels by tiny but measurable amounts. They alter the force between two metal plates placed very close together, an effect called the Casimir effect that has been measured in laboratories. The virtual photon cloud around every charged particle is not a theoretical decoration. It is physically real in its consequences, even though no individual virtual photon can be isolated and observed. The theory that describes all of this, the complete quantum picture of how charged particles interact with the electromagnetic field through the exchange of photons, is called quantum electrodynamics, or QED. This theory was developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, all three of whom shared the Nobel Prize for this work in 1965. QED is arguably the most successful theory in all of physics, measured by the precision of its predictions. It calculates the strength of electromagnetic interactions to extraordinary accuracy, making predictions that agree with experiment to more than 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. No other theory in any branch of science matches this level of agreement between prediction and measurement. At the heart of QED sits charge. Charge is the coupling constant of the theory. It's the number that appears in every calculation of every electromagnetic process. Every time a photon is emitted by a charged particle, the probability of that event depends on the particle's charge. Every time a photon is absorbed, the probability depends on charge. Every time two charged particles exchange a virtual photon and experience a force, the strength of that force depends on the charges of both particles. Charge controls everything. In QED, you can visualize interactions using diagrams called Feynman diagrams, named after Richard Feynman, who invented them. These are simple pictures showing particles as lines and photons as wavy lines. At every point where a particle line meets a photon line, there's a vertex, a junction. This vertex represents the fundamental interaction, a charged particle emitting or absorbing a photon. And at every vertex, the strength of the interaction is determined by the electric charge. The vertex is where charge makes itself felt. It's where the coupling happens. Without charge, there is no vertex. Without the vertex, there is no interaction. Without the interaction, there is no force, no light, no electromagnetic phenomenon of any kind. This framework reveals something profound about the relationship between charge and photons. Photons are massless. They travel at the speed of light. Always. They have zero electric charge themselves. A photon does not interact with other photons directly, at least not at the basic level of the theory. Two beams of light can pass right through each other without scattering or bouncing off each other. This is because photons are the messengers of the electromagnetic interaction, but they don't carry the property that allows them to receive the message. They carry the force, but they don't feel it. They are neutral mediators, delivering the interaction without participating in it themselves. This is different from some other forces in nature. The strong nuclear force, which holds quarks together inside protons and neutrons, is mediated by particles called gluons. But gluons themselves carry a property called color charge, which means they do interact with each other. This makes the strong force much more complicated and very different in character from electromagnetism. Photons, being electrically neutral, keep things comparatively clean. One charged particle emits a photon. Another charged particle absorbs it. That exchange is the force. Now, let's think about what all this means for the question we started with. What is charge made of? We can now see why the question itself is based on a misunderstanding. Charge is not made of anything. Charge is the coupling constant that connects particles to the electromagnetic field. It's the number that appears at every vertex in every Feynman diagram. It's the setting that determines how strongly a particle produces and responds to electromagnetic influence. Asking what charge is made of is like asking what the strength of a bond is made of. The strength isn't made of material. It's a measure of how tightly two things are connected. Charge isn't made of material. It's a measure of how tightly a particle is connected to the electromagnetic field. And this coupling isn't passive. It's dynamic. The electromagnetic field is everywhere, always, and every charged particle is constantly interacting with it. Even a lone electron sitting completely still in otherwise empty space is not quiet. It's constantly emitting and reabsorbing virtual photons. These virtual photons flicker in and out of existence around the electron, creating a cloud of electromagnetic activity. This cloud is not detectable as individual photons, but its cumulative effect is measurable. It slightly shifts the energy levels of atoms. It slightly alters the magnetic properties of particles. These shifts have been measured with extraordinary precision, and they match the predictions of QED perfectly. One of the most famous examples is the anomalous magnetic moment of the electron. According to Paul Dirac's original theory of the electron from the late 1920s, the electron should have a certain magnetic strength. But when physicists measured it precisely, they found it was slightly different from Dirac's prediction. QED explains the difference. The cloud of virtual photons surrounding the electron slightly modifies its magnetic properties. The correction is small but measurable, and QED predicts this correction with an accuracy of better than 1 part in a trillion. This is the most precisely tested prediction in the history of science, and it comes directly from understanding charge as a coupling to the quantum electromagnetic field. The virtual photon cloud, the quantum fluctuations of the field, the tiny corrections to measurable properties, all of this arises because charge connects the electron to the electromagnetic field. There's something else worth appreciating about how charge relates to force. We often talk about charged particles attracting or repelling each other as if the force were a direct connection between the two particles. Electron pushes electron, proton pulls electron. But in the field picture, and especially in the quantum picture, this is not what happens. No particle ever directly touches or pushes another particle. Instead, one particle creates a disturbance in the electromagnetic field. That disturbance propagates through the field. The other particle responds to the disturbance when it reaches that particle's location. The field is the intermediary. The field carries the interaction. This means that electromagnetic forces are not instantaneous. They travel at the speed of light. If you suddenly placed a charged particle at some location, its electric field would not appear everywhere in the universe at once. Instead, the disturbance in the electromagnetic field would propagate outward from that location at 300,000 kilometers per second. A particle 1 light second away would not feel the new charge's field for 1 full second. A particle 1 light year away would not feel it for 1 year. The field carries information at the speed of light, and no faster. This is consistent with Einstein's special relativity, which forbids anything, including forces and information, from traveling faster than light. In the quantum version, this translates into the exchange of virtual photons, which also propagate at or below the speed of light. The force has a finite speed. It takes time to travel from one particle to another. The electromagnetic field is the medium through which this information and this force propagate. And charge is what allows a particle to send and receive these signals. Let me bring this back to everyday experience for a moment, because it's easy to lose the forest for the quantum trees. Every time you see something, you're watching charged particles interact with the electromagnetic field. Electrons in a lamp filament drop to lower energy states and emit photons. Those photons propagate as ripples in the electromagnetic field until they reach your eye, where they're absorbed by charged particles in the cells of your retina, triggering a chemical cascade your brain interprets as sight. Every step in that process, the emission, the propagation, the absorption, depends on charge. If any particle in this chain lacked charge, the chain would break. You would see nothing. Every chemical reaction you've ever witnessed is the electromagnetic field at work. When wood burns, electrons in the wood's molecules interact with oxygen molecules through electromagnetic forces. The bonds rearrange. Energy is released as heat and light, both of which are electromagnetic phenomena. When you digest food, enzymes catalyze reactions by bringing charged and polar molecules into the right configurations, all governed by electromagnetic forces between charged particles. When your muscles contract, charged ions flow across cell membranes, triggering a cascade of electromagnetic interactions that cause protein fibers to slide against each other. All of this comes back to charge. All of it comes back to particles coupling to the electromagnetic field. Even the solidity of objects is electromagnetic. When you press your hand against a table, the table feels solid. It resists your push. But the atoms in your hand and the atoms in the table never actually touch. What resists your push is the electromagnetic repulsion between the electron clouds of your atoms and the electron clouds of the table's atoms. The electrons in your skin have negative charge. The electrons in the table's surface have negative charge. Like charges repel. When you push against the table, you're pushing against the electromagnetic field generated by trillions of charged particles. The feeling of solidity is the feeling of electromagnetic repulsion between charged particles, mediated by the exchange of virtual photons across the boundary between your skin and the table. And what about the fact that opposite charges attract, while like charges repel? This is one of those facts that seems so basic it barely requires explanation. Positive attracts negative. Negative repels negative. Everyone knows this. But why? What makes opposite charges attract and like charges repel? In the classical picture, this is simply built into the mathematical structure of the electromagnetic force law. The force between two charges is proportional to the product of their charges. If the charges have the same sign, the product is positive and the force is repulsive. If the charges have opposite signs, the product is negative and the force is attractive. But this is a description, not an explanation. It tells you what happens, not why. In QED, attraction and repulsion both arise from the exchange of virtual photons. But the details of how the photon exchange produces attractive versus repulsive effects depend on the full quantum mechanical calculation. The mathematics involves summing over all possible ways virtual photons can be exchanged between two particles, accounting for the quantum phases and amplitudes of each process. When the charges have the same sign, the sum produces a net outward push. When the charges have opposite signs, the sum produces a net inward pull. The mechanism is the same, photon exchange, but the outcome differs depending on the signs of the charges involved. This is deeply connected to the structure of the theory itself. QED has a mathematical symmetry built into it. The theory is invariant under a certain kind of transformation involving the phase of quantum fields. This symmetry, called gauge symmetry, is what requires the electromagnetic field and the photon to exist in the first place. Without the symmetry, the theory wouldn't be mathematically consistent. The photon exists because the symmetry demands it. And charge is the quantity that generates this symmetry. Charge is the generator of electromagnetic gauge transformations. This is one of the deepest statements in all of theoretical physics. Charge isn't just a label that determines how strongly a particle feels the electromagnetic field. Charge is intimately connected to the very symmetry that gives rise to the electromagnetic field. The field exists because of the symmetry. The symmetry is generated by charge. Pull any one piece out and the entire structure collapses. So when you ask what charge is made of, you're asking the wrong question, but you're pointing in the right direction. Charge isn't made of anything, but it's connected to everything electromagnetic in the universe. It's the coupling constant of QED. It's the generator of gauge symmetry. It's the property that determines whether a particle talks to the electromagnetic field or passes through it like a ghost. It's the quantity that appears at every vertex of every Feynman diagram, describing every electromagnetic process that has ever occurred or will ever occur. And the value of that coupling, the specific numerical strength of the electromagnetic interaction, is one of the most precisely known numbers in all of physics. Physicists express it as a dimensionless number called the fine structure constant, approximately 1 divided by 137. This number governs the strength of all electromagnetic interactions. It determines how tightly electrons are bound to nuclei. It determines the rates of all electromagnetic processes. It determines the structure of the periodic table of elements. If this number were significantly different, the universe would look completely different. atoms might not form, chemistry might not work, stars might not shine, life as we know it might not exist. Nobody fully understands why the fine structure constant has the value it does. It's one of the deep, open questions in physics. We can measure it with extraordinary precision. We can use it to make predictions that agree with experiment to many decimal places. But we cannot yet derive it from first principles. It appears to be a fundamental constant of nature, a number built into the universe that we must measure rather than calculate. Some physicists hope that a deeper theory, perhaps a theory of quantum gravity or a grand unified theory, will eventually explain why the fine structure constant has the value it does. But for now, it remains one of the irreducible facts about our universe, a number that shapes everything and explains itself to no one. What we do know is that charge, this fundamental property that is not a substance, that is not made of pieces, that cannot be divided or extracted, sits at the center of one of the most successful and precisely tested theories in the history of human knowledge. It's the key that locks particles to the electromagnetic field, the bridge between matter and light, the coupling that makes atoms possible, chemistry possible, biology possible, and sight possible. And every single measurable consequence of this coupling, from the deflection of an electron beam to the color of a sunset, from the glow of a distant star to the spark at your fingertip, confirms that charge is exactly what the theory says it is. A fundamental coupling constant. Not a substance, not a fluid, not a tiny particle hiding inside other particles, but a property so basic, so irreducible, and so consequential that without it, the universe as we know it would not exist. There is something about electric charge that you might overlook if you only think of it as a property, as a coupling to the electromagnetic field. Something that makes charge different from most other quantities you encounter in everyday life. And that something is this. Charge is counted. It is not measured the way you measure temperature or weight or speed, where the value can be anything at all, any number on a smooth, continuous scale. Charge comes in exact, identical, indivisible units. Every charge ever detected in isolation is a whole number multiple of one fundamental quantity. You can have 1 unit of charge, or 2, or 3, or 17, or 6 billion, but you cannot have 1.5 units. You cannot have 2.73 units. You cannot have any value that falls between the whole numbers. Charge is quantized. It comes in packets, and every packet is exactly the same size. This fact is so important that it deserves to be stated again in different words. If you could somehow line up every charged object in the universe and measure the electric charge on each one, you would find that every single measurement is an exact integer multiple of a single number. That number is the elementary charge, approximately 1.602 times 10 to the negative 19 coulombs. This is the charge carried by a single proton. The charge on a single electron is the same number, but negative. And every other charge you will ever encounter in nature is built from these units. An object with a charge of positive 5 has exactly 5 more protons than electrons, contributing to its net charge. An object with a charge of negative 12 has exactly 12 more electrons than protons. There are no in-between values. The charge is always a whole number count of elementary units. This is profoundly different from most physical quantities. Mass can take any value at all. There is no fundamental smallest unit that all masses must be multiples of. Length is the same. You can measure any distance, not just whole number multiples of some basic unit. Temperature, at least in classical physics, varies on a perfectly smooth scale with no smallest step. But charge is different. Charge has a smallest step, and every charge in nature lands exactly on one of those steps, never between them. How do we know this? How did physicists discover that charge is quantized? The answer comes from one of the most elegant and painstaking experiments in the history of physics, the Millikan oil drop experiment. In 1909, Robert Millikan and his graduate student Harvey Fletcher began a series of experiments at the University of Chicago that would run for several years and ultimately earn Millikan the Nobel Prize. The idea was beautifully simple. Millikan sprayed tiny droplets of oil from an atomizer into a chamber. These droplets were incredibly small, just a few micrometers across, barely visible even under a microscope. As the droplets were sprayed, some of them picked up electric charge from friction or from exposure to ionizing radiation. The charged droplets then drifted downward through the chamber under the pull of gravity. Now here's the clever part. Millikan placed two metal plates above and below the chamber and connected them to a high-voltage power supply. By adjusting the voltage, he could create a uniform electric field between the plates. This electric field exerted an upward force on the charged droplets, opposing gravity. By carefully adjusting the voltage, Millikan could make a single droplet hover in mid-air. At that point, the upward electric force exactly balanced the downward gravitational force. Since Millikan knew the strength of the electric field and could calculate the mass of the droplet from its size and the density of oil, he could determine the charge on the droplet. He did this hundreds of times. Hundreds of individual droplets, each with a different charge, each measured separately. And when he looked at the results, a remarkable pattern emerged. The charges were not random. They didn't spread out smoothly across a range of values the way you'd expect if charge were a continuous quantity. Instead, the charges clustered at specific values. Every measured charge was very close to a whole number multiple of a single small value. 1 unit, 2 units, 3 units, 4 units, never 1.5, never 2.3, always whole numbers. By 1913, Millikan had refined his measurements enough to determine the value of this fundamental unit with impressive accuracy. His result was within about 1% of the modern accepted value. This was the first direct measurement of the elementary charge, the smallest unit of electric charge that exists freely in nature. And it confirmed what physicists had suspected but couldn't prove. Charge is quantized. It comes in discrete, identical packets. Think about what this means. Every electron in the universe carries exactly one negative unit of elementary charge. Every proton carries exactly one positive unit. Not approximately, exactly. When Millikan measured the charges on his oil droplets, he found they were always integer multiples of this unit because the droplets had gained or lost whole electrons. You can't transfer half an electron. You can't scrape off a fraction of an electron's charge. The electron is indivisible in this respect. It carries its charge as a permanent, irreducible property. You get the whole thing or nothing at all. And the precision with which this has been confirmed is staggering. Modern experiments have measured the elementary charge to better than 1 part in a billion. The electron charge and the proton charge have been compared with extraordinary care, and they are equal in magnitude to at least 1 part in 10 to the 21st power. That means if the proton charge differed from the electron charge by even 1 part in a billion trillion, we would have detected the difference by now. And we haven't. They are equal and opposite to a degree of precision that is almost impossible to convey in everyday language. This equality is not something our theories predict from first principles, at least not within the standard framework of particle physics alone. The electron and the proton are very different particles. The electron is a fundamental particle, a lepton, with no known internal structure. It has a tiny mass, about 1/1836th the mass of a proton. The proton, by contrast, is a composite particle. It's made of 3 quarks held together by gluons through the strong nuclear force. The proton is nearly 2,000 times heavier than the electron. It participates in the strong force. It has internal structure and a measurable size. The electron has none of these features. And yet, the magnitude of the proton's charge is exactly equal to the magnitude of the electron's charge. Exactly. Not almost, not to a good approximation. Exactly. To every decimal place we have ever been able to measure. This is one of the most remarkable coincidences in physics, or rather, it's a sign that something deeper is going on, something that connects the charges of leptons and quarks in a way that the standard model describes but does not fully explain. Let me talk about quarks, because they complicate the charge quantization story in a fascinating way. In 1964, Murray Gell-Mann and, independently, George Zweig proposed that protons and neutrons are not fundamental particles. They are made of smaller constituents called quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. And here's the thing that initially shocked the physics community. Quarks carry fractional electric charges, not whole number multiples of the elementary charge, but fractions. An up quark has a charge of positive 2/3 of the elementary unit. A down quark has a charge of negative 1/3 of the elementary unit. These are fractions. They violate the pattern Millikan observed, at least on the surface. Millikan found that every charge is a whole number multiple of the elementary unit. But quarks carry charges that are 1/3 and 2/3 of that unit. How can both things be true? The resolution is elegant. Quarks are never found alone. They are always confined inside composite particles called hadrons, bound together by the strong nuclear force. The strong force has a peculiar property. It gets stronger as quarks try to separate, not weaker. If you try to pull 2 quarks apart, the energy required grows without limit. Before you can separate them, the energy you've invested creates new quarks from the vacuum, and these new quarks pair up with the originals to form new composite particles. You never end up with an isolated quark. This phenomenon is called confinement. Because quarks are always confined, the charges you actually observe in nature are always the charges of composite particles. A proton has 2 up quarks at positive 2/3 each and 1 down quark at negative 1/3. The total charge is 2/3 plus 2/3 minus 1/3, which equals exactly positive 1. 1 whole elementary unit. A neutron has 1 up quark at positive 2/3 and 2 down quarks at negative 1/3 each. The total charge is 2/3 minus 1/3 minus 1/3, which equals exactly 0. Every combination of quarks that nature allows, every hadron that can exist, has a total charge that is an exact whole number of the elementary unit. The fractional charges of individual quarks always combine to give integer totals. The quarks carry fractions, but you never see the fractions in isolation. You only see the sums, and the sums are always whole numbers. This is why Millikan's experiment found integer multiples. Not because there are no fractional charges in nature, but because the fractional charges are always locked inside composite particles where they add up to integers. The quantization of observable charge is preserved, even though the underlying constituents carry fractions. It is as if nature has a rule. You can use fractional pieces inside, but the final product you show the world must always be a whole number. The books must balance. And they do balance. Not just in static objects sitting there with fixed charges, but in every process, every reaction, every transformation that has ever occurred in the history of the universe. This brings us to one of the most powerful principles in all of physics: charge conservation. Electric charge is conserved. This means that in every physical process, the total electric charge before the process equals the total electric charge after. Charge cannot be created from nothing. Charge cannot be destroyed into nothing. It can move from one particle to another. It can redistribute itself among different objects. But the total amount, the grand sum of all positive and negative charges involved, never changes. Not by 1 unit. Not by a fraction of a unit. Not ever. This has been tested with extraordinary rigor. Every particle collision observed in accelerators, and there have been billions upon billions of them, conserves charge exactly. Every nuclear reaction, every chemical reaction, every atomic transition, every decay of an unstable particle, every creation of new particles from pure energy, all of them conserve charge. Physicists have searched for violations of charge conservation with some of the most sensitive experiments ever devised, and they have found nothing. 0 violations. The upper limits on any possible charge non-conservation are so stringent that if there were even a tiny leak, even the faintest drip of charge being created or destroyed, we would have seen it by now. We haven't. Charge conservation appears to be absolute. Let me give you some concrete examples to make this real. Consider the simplest case, an atom emitting a photon. An electron inside an atom drops from a higher energy level to a lower one and emits a photon, a particle of light. Before the process, you have an atom with some number of protons and electrons. After the process, you have the same atom in a lower energy state plus a photon. What about charge? The atom's charge hasn't changed. The same number of protons and electrons are present, and the photon carries 0 electric charge. Total charge before equals total charge after. Charge is conserved. Now consider a more dramatic example. In particle accelerators, high-energy collisions can create new particles from pure energy. A proton smashes into another proton at nearly the speed of light, and from the energy of the collision, new particles are born. Pions, kaons, other protons, antiprotons, electrons, positrons, and many more exotic particles can emerge from these collisions. The shower of particles can be complex, with dozens of new particles flying in all directions. But if you add up the total charge of everything that came in and compare it to the total charge of everything that came out, the numbers match. Exactly. Every single time. No exceptions have ever been observed. Or consider radioactive decay. A neutron, which has 0 charge, can decay into a proton, an electron, and an antineutrino. The proton has charge +1. The electron has charge -1. The antineutrino has charge 0. Total charge after the decay is +1 - 1 plus 0, which equals 0. Exactly the charge of the original neutron. Charge is conserved. What about pair creation? When a sufficiently energetic photon passes near a heavy nucleus, it can spontaneously convert into a particle-antiparticle pair. For example, a photon can become an electron and a positron. The photon has 0 charge. The electron has charge -1. The positron has charge +1. Total charge after is -1 plus +1, which equals 0. The charge of the original photon. Once again, charge is conserved. The photon had no charge, and the pair it created has no net charge either. You've created charged particles when none existed before, but you've created them in equal and opposite pairs, so the total charge remains unchanged. This is always how it works. Whenever charged particles are created, they are created in combinations that preserve the total charge. Whenever charged particles are destroyed, they are destroyed in combinations that preserve the total charge. The universe keeps a perfect ledger. Every positive charge created is accompanied by a negative charge somewhere. Every negative charge destroyed is matched by a positive charge destroyed alongside it. The books always balance. Always. Why? Why is charge conserved? Is it just an empirical observation? A pattern we've noticed in experiments? Or is there something deeper going on? There is something deeper, and it comes from one of the most beautiful connections in all of theoretical physics: the connection between symmetry and conservation laws. In 1918, the mathematician Emmy Noether proved a theorem that changed how physicists think about the universe. Noether's theorem states that every continuous symmetry of a physical system corresponds to a conserved quantity. If the laws of physics don't change over time, energy is conserved. If the laws of physics are the same everywhere in space, momentum is conserved. If the laws of physics are the same regardless of which direction you're facing, angular momentum is conserved. These are not separate postulates bolted onto the theory. They follow automatically from symmetries. Symmetry in, conservation out. It's a mathematical certainty proven with complete rigor. And the symmetry that gives rise to charge conservation is gauge symmetry. Specifically, the symmetry of the electromagnetic field under a particular kind of transformation. Without going deep into the mathematics, the idea is this. The equations that describe the electromagnetic field and its interaction with charged particles have a freedom built into them. You can shift a certain mathematical quantity related to the phase of the quantum field by any amount at any point in space, and the physics doesn't change. The equations remain the same. The predictions remain the same. Nothing observable changes. This is electromagnetic gauge symmetry. Noether's theorem tells us that this symmetry, this invariance under gauge transformations, implies a conserved quantity. And that conserved quantity is electric charge. Charge conservation is not an accident. It's not a coincidence. It's not something that just happens to be true based on observations. It's a mathematical consequence of a deep symmetry in the laws of physics. The symmetry demands it. If the symmetry holds, charge must be conserved. Period. This is one of the most profound things about charge. Its conservation is linked to the very structure of the electromagnetic field. The same symmetry that requires the electromagnetic field to exist and requires photons to be massless also requires charge to be conserved. These aren't separate facts. They're different facets of the same underlying mathematical structure. The electromagnetic field, the photon, charge quantization as observed in composite particles, and charge conservation are all woven together into a single coherent framework. Charge conservation is not a rule imposed on top of the laws of physics. It is built into the laws of physics at the most fundamental level. You cannot write down a mathematically consistent theory of the electromagnetic field without charge conservation falling out automatically. The symmetry is so deeply embedded that violating charge conservation would require violating the symmetry. And violating the symmetry would destroy the mathematical consistency of the theory. Remove charge conservation and the theory falls apart. This is why physicists are so confident that charge conservation is exact, not approximate. Not mostly true, not true to some very good precision, exact. Because it follows from a symmetry, and symmetries in physics are either exact or broken. If electromagnetic gauge symmetry is exact, and all evidence says it is, then charge conservation is exact. There are no loopholes. There are no exceptions. The total charge of the universe, whatever it is, has been exactly the same since the beginning of time, and will remain exactly the same until the end. And here is something remarkable to contemplate. The total electric charge of the observable universe appears to be 0, or very close to 0. For every proton, there seems to be an electron. For every positive charge, a negative charge. The universe appears to be electrically neutral overall. This makes sense in the context of charge conservation, combined with the early history of the cosmos. If the universe began with 0 total charge, and charge is conserved, then the total charge must still be 0. Every positive charge that has ever been created was accompanied by a negative charge. Every particle-antiparticle pair that emerged from the energy of the early universe came in charge-balanced pairs. The total never shifted from zero. This means that every charge you see around you, every electron in your body, every proton in every atom of every star, is balanced by an equal and opposite charge somewhere else. The charges in your body are balanced by charges in the air, in the ground, in distant galaxies. The grand total is zero. The universe created charged particles in enormous quantities, but it created them in perfect balance. The positive charges and the negative charges sum to nothing. The ledger is clean. Think about how astonishing this is from a bookkeeping perspective. The observable universe contains roughly 10 to the 80th protons and a similar number of electrons. That is an enormous number. A 1 followed by 80 zeros. And the total positive charge and total negative charge match to extraordinary precision. Every proton is balanced by an electron somewhere. Every positive charge is cancelled by a negative charge. Across the entire observable universe, across 93 billion light-years of space, across nearly 14 billion years of cosmic history, the books balance. And this balance is maintained not by some cosmic accountant checking the numbers. It's maintained automatically by the laws of physics themselves, by the gauge symmetry of the electromagnetic field, by Noether's theorem, by the deep mathematical structure of the theory. The universe doesn't need to try to conserve charge. It can't help it. Conservation is built in. It would take a violation of the fundamental symmetries of nature to create even 1 unit of net charge from nothing. And as far as we can tell, those symmetries are never violated. This brings us to a subtlety that is worth appreciating. Charge conservation and charge quantization are related, but they are not the same thing. Conservation says the total doesn't change. Quantization says the individual values come in discrete units. Both are observed, both are important, but their theoretical origins are different. Conservation follows from gauge symmetry through Noether's theorem. Quantization of observable charge, the fact that every isolated charge is an integer multiple of the elementary charge, is a consequence of how quarks combine and the confinement of the strong force. There is an additional, deeper layer. In 1931, the physicist Paul Dirac showed that if magnetic monopoles exist, isolated north or south magnetic poles without a matching opposite pole, then charge quantization would follow automatically from the mathematics of quantum mechanics and electromagnetism. A magnetic monopole has never been found. But if one existed anywhere in the universe, even just one, the mathematics requires that all electric charges everywhere must be exact multiples of a fundamental unit. This is a beautiful result. It would explain why charge is quantized, connecting it to the possible existence of magnetic monopoles. Some grand unified theories predict that monopoles should exist, created in the early universe, but we have not detected any. Without monopoles, the Standard Model by itself does not fully explain why charge is quantized at the level of quarks. It describes quarks as having charges of 2/3 and -1/3, but it takes these values as inputs. The theory doesn't derive them from a deeper principle within its own framework. The quantization is observed, it's confirmed, it's used in calculations with tremendous success, but the ultimate reason for the specific fractional values remains an open question, one that points toward physics beyond the Standard Model. What we can say with complete confidence is this: in every experiment ever performed, charge has been conserved. In every measurement ever made, charge has been quantized in units consistent with the elementary charge and the fractional charges of quarks. These two facts, conservation and quantization, are among the most solidly established in all of science. They have survived every test, withstood every challenge, and held up under scrutiny of the most extreme precision. They are cornerstones of our understanding of the physical world, and they both point back to the same conclusion we've been building toward throughout this story. Charge is not a substance that can be divided, diluted, or destroyed. It is a fundamental property that comes in fixed units and obeys absolute conservation laws. It cannot be created from nothing. It cannot be destroyed into nothing. It can be transferred. It can be rearranged. But the total never changes. The universe is meticulous about this. It never rounds. It never approximates. It never borrows or lends. The charge you have is the charge you keep, unless you pass it to someone else. And when you do, the total remains the same. Every spark at a doorknob conserves charge. Every bolt of lightning conserves charge. Every nuclear reaction in the core of a star conserves charge. Every collision in a particle accelerator conserves charge. Every chemical reaction in every cell of your body conserves charge. This is not a pattern that occasionally holds and occasionally breaks. It is a law of nature, rooted in symmetry, confirmed by experiment, and woven into the mathematical fabric of reality itself. The standard model of particle physics is the most comprehensive and precisely tested theory of matter and forces ever constructed. It catalogues every known fundamental particle and describes 3 of the 4 fundamental forces. And woven into its structure, written into its equations at the deepest level, are the electric charge assignments of every particle in the universe. These assignments are not arbitrary. They follow patterns. They obey constraints. They fit together with a precision that borders on mathematical inevitability. And yet, at the very bottom of the explanation, there is a mystery that remains unsolved. Let me walk you through the particle zoo and show you how charge is distributed across the fundamental building blocks of nature, because the pattern itself is striking, and understanding it brings us closer to the deepest questions physics can ask about charge. Start with the leptons, the family of particles that includes the electron. There are 6 leptons in total, arranged in 3 generations. The first generation contains the electron with a charge of -1 and the electron neutrino with a charge of 0. The second generation contains the muon, also with a charge of -1, and the muon neutrino with a charge of 0. The third generation contains the tau, again with a charge of -1, and the tau neutrino, again with a charge of 0. The pattern is perfect. Every charged lepton has exactly -1 unit of charge. Every neutrino has exactly 0. No variation, no exceptions. 3 copies of the same charge structure, differing only in mass. Now the quarks. There are also 6 quarks, also arranged in 3 generations. The first generation contains the up quark with a charge of +2/3 and the down quark with a charge of -1/3. The second generation contains the charm quark at +2/3 and the strange quark at -1/3. The third generation contains the top quark at +2/3 and the bottom quark at -1/3. Again, the pattern repeats 3 times. Every up-type quark has exactly +2/3. Every down-type quark has exactly -1/3. These numbers are peculiar. Why 2/3 and 1/3? Why not 1/2 and 1/2? Why not 1 and 0, matching the leptons? The fractional values seem oddly specific, and yet they are precisely the values needed to make the theory work. Here is one of the most striking constraints. Within each generation, the charges of the leptons and quarks are related in a very specific way. Take the first generation. The electron has charge -1. The electron neutrino has charge 0. The up quark has charge +2/3. The down quark has charge -1/3. But quarks come in 3 copies, 3 so-called colors, which I'll explain in a moment. So effectively, within each generation, you have 1 electron at -1, 1 neutrino at 0, 3 up quarks each at positive 2/3, and 3 down quarks each at negative 1/3. Add up all the charges in the generation. -1 plus 0 plus 3 times 2/3 plus 3 times negative 1/3. That's -1 plus 0 plus 2 minus 1. Total equals 0. The sum is 0. The charges within each generation cancel perfectly. This is not a coincidence, it's a requirement. The mathematical consistency of the Standard Model demands it. Without this cancellation, the theory would produce nonsensical results. Certain calculations would give infinite answers that cannot be removed. These problematic infinities are called anomalies, and the condition that eliminates them is called anomaly cancellation. The charges of the quarks and leptons must be precisely what they are, in exactly these ratios and with exactly these multiplicities, for the theory to be mathematically consistent. This is remarkable. The charge of the electron, -1, is locked to the charges of the quarks, 2/3 and 1/3, by a mathematical requirement. If the electron had a slightly different charge, even by the tiniest amount, while the quark charges stayed the same, the Standard Model would be mathematically inconsistent. The calculations would produce infinities. Probabilities would come out negative. The theory would collapse. The specific charge values are not free parameters the universe could have chosen at random. They are constrained by the internal logic of the theory. Let me make this more concrete, because anomaly cancellation sounds abstract, but its consequences are vivid. In quantum field theory, you calculate the probability of a process happening, say, 2 electrons scattering off each other. The calculation involves summing over all the possible ways the process could occur, including contributions from virtual particles circulating in loops. These loop contributions are where anomalies hide. If the charges of the particles running in those loops don't satisfy certain precise relationships, the sums produce results that are mathematically catastrophic. Not just wrong, but incoherent. You might calculate a probability and get a number greater than 1, which is nonsensical, since a probability cannot exceed 100%. Or you might find that a quantity that must be positive comes out negative. Or you might find that the answer depends on how you set up the calculation, giving different results depending on which mathematically equivalent method you choose. Any theory that does this is not just inaccurate, it is meaningless. It makes no definite predictions at all. The extraordinary thing is that the charges of the quarks and leptons in our universe are exactly the values that make all of these pathologies cancel. The dangerous loop contributions from quarks cancel against the dangerous loop contributions from leptons, term by term, generation by generation, leaving a theory that is perfectly well behaved. The charges aren't just convenient, they are necessary. Change the electron's charge by even the smallest fraction while leaving everything else the same, and the cancellation fails. The theory stops making sense. This means the charge of the electron is not independent of the charges of the quarks. They are locked together by a mathematical requirement as rigid as any equation in physics. The universe didn't pick these numbers from a hat. These numbers are among the very few that allow a consistent theory to exist at all. But this raises an even deeper question. Why does the Standard Model have the particular mathematical structure that imposes these constraints? The Standard Model is built on a specific combination of symmetry groups. These groups, called SU3, SU2, and U1, govern the three forces the theory describes. SU3 describes the strong nuclear force and the color charge of quarks. SU2 describes the weak nuclear force. And U1 is the symmetry associated with electric charge and the electromagnetic field. The full structure of the Standard Model is a product of these three groups, and the charge assignments of all particles are determined by how they transform under these symmetries. Electric charge in this framework is not entirely a standalone quantity. It's actually a combination of two more fundamental numbers, weak isospin and weak hypercharge that are related to the SU2 and U1 symmetries. When the Higgs field, whose existence was confirmed in 2012 through the discovery of the Higgs boson at the Large Hadron Collider, takes on its particular value throughout space, it breaks the SU2 and U1 symmetries in a specific way, and the surviving unbroken symmetry is the U1 of electromagnetism. The electric charge of each particle is determined by its weak isospin and weak hypercharge values, combined according to a specific formula. So the charges we observe are not fundamental inputs to the theory. They're consequences of deeper quantum numbers and the way the Higgs field breaks the symmetry. This is beautiful, but it also means the question has shifted. Instead of asking why the electric charges have the values they do, we now ask why the weak isospin and hypercharge assignments are what they are. And the standard model doesn't answer that. It takes those assignments as given. They're inputs, not outputs. The theory tells you what happens given these charge assignments. It doesn't tell you why nature chose these particular values over any other mathematically possible set. This is one of the places where the standard model, despite its extraordinary success, reaches its limits. It describes and predicts with breathtaking precision, but the charge assignments are among the things it requires for consistency without fully deriving from first principles. It does not uniquely predict them in the way it predicts, say, the probability of a particular scattering process. Grand unified theories attempt to go deeper. These are theories that propose the three forces of the standard model: the strong force, the weak force, and electromagnetism, are actually different aspects of a single unified force at very high energies. At the energy scales we probe in our experiments, the three forces appear distinct. They have different strengths, different properties, different symmetry structures. But grand unified theories suggest that at much higher energies, far higher than any accelerator can reach, the three forces merge into one. The three symmetry groups combine into a single, larger symmetry group. In 1974, Sheldon Glashow and Howard Georgi proposed one of the first grand unified theories, based on the symmetry group SU5. In this theory, quarks and leptons are placed together in the same mathematical structure. They're different aspects of the same underlying particle type, and because they're unified, their charges are related. The charge of the electron is connected to the charges of the quarks by the structure of the larger symmetry group. The specific values, -1 for the electron, +2/3 and -1/3 for the quarks, emerge naturally from how the particles fit into the representations of SU5. To understand what this means intuitively, think about what happens as you increase the energy of particle interactions. At the energies we experience in daily life, and even at the energies inside particle accelerators, the three forces look completely different. Electromagnetism has infinite range, and its force carrier, the photon, is massless. The weak force has extremely short range, and its carriers, the W and Z bosons, are heavy. The strong force is powerful at close range, but doesn't reach beyond the confines of a proton. They seem like three unrelated phenomena. But as you push to higher and higher energies, these differences start to dissolve. The strengths of the three forces, which are so different at low energies, gradually converge. They approach each other, getting closer and closer as the energy climbs, until, at an extraordinarily high energy, roughly 1 trillion times greater than the energy accessible at the Large Hadron Collider, the three strengths meet. They become equal. The three forces become one force. The distinction between quarks and leptons fades. A quark and an electron become different states of the same underlying entity, the way ice and steam are different states of the same substance. At that unification energy, asking whether something is a quark or a lepton is like asking whether water is ice or steam. The question only makes sense at lower temperatures, where the symmetry is broken and the states look different. At the unification scale, they are the same thing. And because they are the same thing, their charges must be related by the symmetry that connects them. The electron's charge of -1 and the quark charges of 2/3 and -1/3 are not independent choices. They are locked together by the structure of the unified group, different projections of the same underlying quantity. This is a profound result. If grand unification is correct, the seemingly arbitrary charge values of the standard model are not arbitrary at all. They're determined by the structure of a single larger symmetry. The electron's charge equals exactly -1 elementary unit because the electron and the quarks are different faces of the same coin, related by a symmetry that fixes their charges relative to each other. The quantization of charge, the fact that all charges are multiples of 1/3, follows automatically from the group theory. You don't need magnetic monopoles or any other exotic mechanism. The grand unified symmetry does the job by itself. Other grand unified theories based on larger groups like SO10 go even further. They can unify all the particles of a single generation into one mathematical object. All the quarks and leptons, along with their antiparticles, fit into a single representation of SO10. The charge assignments, the masses, even the number of generations might eventually be explained by the structure of the theory. But grand unified theories remain unproven. They make predictions. The most dramatic is proton decay. If quarks and leptons are unified, then under certain rare circumstances, quarks can transform into leptons. This means protons, made of quarks, should eventually decay. The predicted lifetime is extremely long, perhaps 10 to the 34th years or more, far longer than the age of the universe. But if you watch enough protons, you might catch one decaying. Experiments have been searching for proton decay for decades, using enormous underground detectors filled with thousands of tons of water. So far, no proton decay has been observed. These experiments are monuments to patience. The Super Kamiokande detector in Japan, for instance, sits 1 kilometer underground to shield it from cosmic rays that would create false signals. Inside the cavern is a tank containing 50,000 tons of ultra-pure water, surrounded by over 11,000 light sensors, each one capable of detecting a single photon. The idea is simple in principle. If a proton in one of the water molecules decays, the decay products will travel faster than light moves through water, and that will produce a faint cone of blue light called Cherenkov radiation. The sensors watch for that flash, and they watch constantly, every second of every day, year after year. Decades of watching. Trillions of protons sitting in that tank, and not once has any of them been caught decaying. The sheer scale of the experiment and the depth of its patience tell you something about how seriously physicists take the question of charge. If proton decay were observed, it would be direct evidence that quarks and leptons are unified, that their charges are related by a grand symmetry, that the specific values of electric charge are not arbitrary inputs, but necessary consequences of a deeper structure. The fact that no decay has been seen doesn't rule out grand unification. It rules out the simplest versions and pushes the unification energy higher, the proton lifetime longer, the experiment harder. The current experimental limits push the proton lifetime above 10 to the 34th years, which rules out the simplest grand unified models. More elaborate versions survive, but the direct evidence remains elusive. So the deepest question about charge, why do particles carry the specific charge values they do, remains open. The standard model constrains the values through anomaly cancellation. Grand unified theories would explain them through larger symmetry structures, but neither has delivered a complete, experimentally confirmed answer. Charge quantization is observed. It's built into the framework. It's necessary for mathematical consistency. But the ultimate origin of the specific values remains one of the great open questions in fundamental physics. Physics is honest about this. It measures charge with extraordinary precision. It uses charge to make predictions of extraordinary accuracy. But it does not claim to have the final word on why charge takes the values it does at the deepest possible level. Now let me broaden the picture, because electric charge is not the only kind of charge in physics. The word charge in particle physics refers to any fundamental property that determines how a particle couples to a particular force. Electric charge couples particles to the electromagnetic field, but there are other fields, other forces, and other charges. The strong nuclear force, the force that holds quarks together inside protons and neutrons, has its own charge. It's called color charge. Color charge has nothing to do with actual colors. The name is a metaphor borrowed from the color wheel, because color charge comes in 3 types, whimsically labeled red, green, and blue. Every quark carries one of these 3 color charges. Antiquarks carry the corresponding anti-colors, and gluons, the particles that mediate the strong force the way photons mediate the electromagnetic force, carry combinations of color and anticolor. Color charge works in many ways like electric charge, but with crucial differences. Like electric charge, color charge is conserved. The total color going into any reaction equals the total color coming out. Like electric charge, color charge determines coupling to a field. A quark's color charge determines how strongly it interacts with the gluon field. Like electric charge, color charge is quantized. But unlike electric charge, which comes in positive and negative, color charge comes in 3 types plus their antiversions. And unlike photons, which carry no electric charge and therefore don't interact with each other through electromagnetism, gluons carry color charge and do interact with each other through the strong force. This self-interaction makes the strong force much more complex than electromagnetism and is ultimately responsible for confinement, the phenomenon that prevents quarks from ever being isolated. The weak nuclear force, responsible for certain radioactive decays, has its own charge too. It's called weak isospin. Every particle that participates in the weak force carries weak isospin. The electron has it, the neutrino has it, quarks have it, photons don't. The Higgs boson interacts with it. Weak isospin determines how strongly a particle couples to the W and Z bosons, the particles that mediate the weak force. So when physicists talk about charge in the most general sense, they're talking about a fundamental coupling, a property that connects a particle to a specific force field. Electric charge couples to the electromagnetic field. Color charge couples to the strong field. Weak isospin couples to the weak field. Each charge is a property, not a substance. Each charge is quantized. Each charge is conserved. Each charge determines whether and how a particle participates in the corresponding interaction. The concept of charge, in this broader sense, is one of the most powerful organizing principles in all of physics. It tells you which particles talk to which fields and how loudly. And there's a deep structural similarity across all these charges. Each one is associated with a symmetry. Electric charge is associated with electromagnetic gauge symmetry. Color charge is associated with the gauge symmetry of the strong force. Weak isospin is associated with the gauge symmetry of the weak force. In each case, the symmetry determines the structure of the force, the existence of the mediating particles, and the conservation of the charge. Noether's theorem applies to all of them. Symmetry guarantees conservation. The framework is universal. This universality suggests that at some level, all these charges might be aspects of a single, deeper structure. That's exactly what grand unification proposes. At sufficiently high energies, the separate charges merge. Color charge, weak isospin, and electric charge become different components of one unified charge, the way 3 separate streams might join into a single river. The apparent diversity of charges at low energies reflects a broken symmetry, like the river splitting into separate streams as it flows downstream. At the source, there's one current. At our energy scale, we see three. Whether this is actually how nature works remains to be seen, but the conceptual pattern is compelling. Charge, in every case we've encountered, is a fundamental property that couples a particle to a field. It's always quantized. It's always conserved. It's always tied to a symmetry. These features repeat across every force we know, and the repetition suggests that charge, in this deep sense, is not just an incidental feature of particles, but one of the organizing principles of reality itself. Let me close by bringing everything together and reflecting on what we've learned. We started with a simple question: what is charge made of? And we discovered that the question itself contains a hidden assumption. It assumes charge is made of something, that it has ingredients, that it's a substance you could analyze and decompose. But charge is not that kind of thing. Charge is a property, a fundamental, irreducible, permanent property of certain particles. It's not made of smaller pieces. It's not a fluid that flows or a material that accumulates. It's a number, a quantum number, that tells the universe how a particle relates to the electromagnetic field. It determines whether a particle can emit and absorb photons. It determines how strongly a particle pushes and pulls on other charged particles. It determines whether a particle participates in the vast web of electromagnetic interactions that holds atoms together, drives chemistry, powers stars, and allows you to see. This property is quantized. It comes in exact, identical units. Every electron has the same charge. Every proton has the same magnitude of charge, opposite in sign. Every quark carries its precise fraction. No variation, no imperfection, no exceptions have ever been found. This property is conserved. In every process ever observed, the total charge before equals the total charge after. This conservation follows from a deep symmetry of the electromagnetic field, a symmetry so fundamental that violating charge conservation would require breaking the mathematical structure of the theory itself. This property determines the coupling between particles and the electromagnetic field, with the coupling mediated by photons. Every electromagnetic process, from a spark to a sunset, from a chemical reaction to the glow of a distant star, traces back to charge. Without it, the electromagnetic field would exist, but have nothing to talk to. Photons would propagate through an empty cosmos with no particles capable of emitting or absorbing them. Light would travel forever through a universe that could neither produce it nor see it. And the specific values of charge, the exact numbers that nature assigns to each type of particle, are constrained by the mathematical consistency of the standard model, and might ultimately be explained by a larger, unifying symmetry. But at the present frontier of human knowledge, the final reason for these specific values remains an open question. Physics is honest about the boundaries of what it knows. It can measure charge to 12 decimal places. It can predict electromagnetic processes to extraordinary accuracy. But it cannot yet point to a single principle and say, this is why the electron has exactly this charge and no other. That honesty is part of what makes the story so compelling. Science does not pretend to have all the answers. It distinguishes between what it has proven, what it strongly suspects, and what it does not yet know. The nature of charge falls into all three categories simultaneously. We know with absolute certainty that charge is a conserved, quantized property. We strongly suspect that its specific values arise from a deeper symmetry yet to be fully uncovered. And we openly acknowledge that the final explanation lies beyond our current reach. There's something deeply satisfying about this picture, even with its unresolved questions, because it shows that the universe is not built from stuff all the way down. At the deepest level physics has reached, the building blocks of reality are not tiny objects made of tinier objects, made of still tinier objects in an infinite regression. The building blocks are properties, relationships, couplings, numbers that describe how fundamental entities relate to fundamental fields. Charge is not a thing inside a particle. It's a feature of the particle's identity, as intrinsic as existence itself. And from this single feature, from this one number written into the identity of an electron, an entire universe of phenomena unfolds. The attraction that binds electrons to nuclei and makes atoms possible. The bonds that link atoms into molecules and make chemistry possible. The forces that fold proteins and drive the molecular machinery of life. The currents that flow through your nervous system and make thought possible. The light that crosses billions of light years of space from distant galaxies to the lenses of our telescopes. All of it comes from charge. All of it comes from a property that has no size, no weight, no color, no shape, no material composition of any kind. The next time you flip a light switch and a room fills with light, you're watching charge at work. Electrons in the wire, carrying their negative charge, drift under the influence of an electromagnetic field. They reach the filament or the semiconductor in the bulb. They interact with the electromagnetic field, emitting photons. Those photons, massless quanta of the electromagnetic field, race across the room at 300,000 kilometers per second and are absorbed by charged particles in the cells of your retina. Every link in that chain, from the power plant to your conscious perception of light, is governed by charge, by a property, not a substance, not a material, a property. And that property is the same everywhere. The charge of an electron in your light bulb is the same as the charge of an electron on the other side of the galaxy, the same as the charge of an electron in a star that burned out before the Earth was born, the same as the charge of an electron that will exist in a star that hasn't formed yet. The uniformity is absolute. The permanence is complete. In a universe where almost everything changes, where stars are born and die, where galaxies merge and drift apart, where species evolve and go extinct, where mountains rise and erode and continents shift, charge remains the same. It was what it is now at the beginning. It will be what it is now at the end. It is one of the fixed points of reality, a constant in a cosmos defined by change. What is charge made of? Nothing. It's not made of anything, and that's precisely what makes it so extraordinary. It's a property so fundamental that it doesn't need to be made of smaller pieces. It doesn't need to be assembled from ingredients. It simply is. And from that bare existence, from that single quantum number etched into the identity of a particle, the entire electromagnetic universe unfolds. Light, heat, chemistry, life, sight, thought. All of it, every photon, every spark, every signal in every nerve, flowing from a property that has no substance and no size. A number, a coupling, a relationship between a particle and a field, the deepest label in physics, and one of the most consequential facts about the universe we inhabit.